Check it out now, y'all.
nanoHUB-U, online instruction.
Hello and welcome to Lecture 2, Week 1 of Dynamic Atomic Force Microscopy Methods. In the last class, we had talked about a few key concepts introducing dynamic atomic force microscopy. The first was the fact that in AFM, we're interested in interaction forces between a few atoms on the tip of an AFM probe and a few atoms on the surface. These forces not only allow us to image samples with very high resolution, but they are of inherent interest just to understand surface physics and properties on the surface themselves. As one tries to measure the tip-sample interaction forces as a function of the gap d between the lowermost atoms on the tip and the highermost atoms on the surface, one can use static AFM methods, which we talked about in the first part of the class. But there are three key disadvantages when one does so. The first being the fact that there's a range of D values or gap values that are not accessible due to cantilever snap-in and pull-off in a static force distance curve experiment. The second disadvantage is the fact that a static force distance experiment is not able to distinguish between a snap-in and pull-off that occurs due to the normal canonical attractive repulsive interaction force as opposed to an interaction force which is truly hysteretic, for example, due to capillary forces when the tip comes and moves away from the sample. A third important relevant disadvantage of static AFM methods is when one uses static AFM for scanning purposes, like in contact mode scanning. One tends to apply constant lateral forces which could easily move weakly bonded samples, and it'll be very hard to image weakly bonded samples in that case. This is historically the reason why dynamic atomic force microscopy was developed in the first place. And the principle of measuring forces here is completely different. What one does is one mechanically excites a cantilever at resonance and looks at changes in the amplitude and phase of the oscillator due to the interaction forces to really understand what those forces are and to image the sample with high resolution. Key to understanding dynamic atomic force microscopy is to understand the effect that the forces, the tip-sample interaction forces, have on the oscillator's dynamics. So we have to understand and model the probe itself. And the simplest model, which is the point mass oscillator model, which was introduced in the last lecture, can be made fairly rigorous by applying an energy equivalence principle, which requires, amongst other things, that the kinetic energy of the actual probe be equal to that of the point mass oscillator, and the same with the potential energy. What this leads to are equivalent properties of the effective masses, effective mass of this point mass oscillator, and the effective stiffness of the point mass oscillator, and the effective damping, that ensure this equivalence in a manner that the point mass oscillator would actually oscillate in a manner exactly the same as the actual probe. So, in the process of doing this effective values, it was clear that, for example, the effective mass of this point mass oscillator would not be equal to the actual mass of the tip of an AFM cantilever, but rather it would be some combination of the tip mass and something else that measures the distribution of mass along the length of the cantilever itself. We are going to begin today's lecture by talking about the transient oscillations of the probe. Our eventual goal, of course, is to get from transient oscillations to understanding the response of the probe in the presence of tip-sample interaction forces, in the presence of excitation forces as well. But for the moment, let us remove all external forces and just try to understand what happens to the dynamics of the probe just as is. The equation of motion that governs the transient motion of this probe is equation 1. This was derived last time by applying Newton's laws to the point mass particle. When we divide through this equation by K, the effective stiffness of the probe, effective spring constants of the probe, we can define the fundamental frequency, natural frequency omega naught, which is square root K over M. That's an angular frequency in radians per second. There's a Q factor, which is a combination of mass, stiffness, and damping. We can also define a natural frequency in hertz as omega naught divided by 2 pi. The fundamental time period of oscillation of this oscillator is 2 pi divided by omega 0. Equation 1 has a closed-form analytical solution which takes into account the initial conditions of the equation. It's a second-order linear autonomous equation, as I discussed last time. And initial conditions for solving that differential equation require a prescription of the original displacement at time t equal to 0, so q at 0. But you also need to know what the velocity of the probe is at time t equals 0, which is q dot at 0. So when you put it together and try to solve that equation 1, it turns out there are two important conditions which determine what form the solution actually takes. The details of the derivation are actually provided in the appendix on this lecture, at the back of this lecture. First case is when the Q factor, the quality factor of resonance, is greater than 1/2. In this case, we get what are called a exponentially decaying oscillations. This is also called an underdamped condition, which is shown in equation 3. Case 2 is when Q is less than half, and this is called an overdamped condition, where you get an exponential decay without any oscillation. To understand the mathematical nature of these two equations written here, if you look at equation 3, there is an exponentially decaying term that lies outside the parentheses. And inside the parentheses, you've got a combination of a sine and a cosine of the same frequency, which of course can be combined and written as a sine wave of the same frequency, but with some phase shift. So what's inside the parentheses is a nice harmonic sine or cosine wave. What's outside the parentheses is an exponentially decaying term. So the product of the two is going to give a variation of tip displacement that is an oscillatory decay with time. In the case 2, equation 4, there are two terms in the solution. Both happen to be purely exponential terms with no sines or cosines involved in them. If one looks at the power of the exponent, it turns out that in both cases you have negative powers to the exponent, which means that you have two exponential terms with negative powers, which cause the solution to decay without any oscillation. We can rewrite equation 3 for an initial displacement of 0 to try to understand what's the physical meaning of this solution. And when one does that, one gets equation 5. Again, it's easy to see the mathematical form, and by looking at equation 5, you can easily judge that in the underdamped case, you've got this exponentially decaying solution. In the overdamped case, you're going to get no oscillation, but just a decay down to 0. There are two important observations from equation 5. The first is that the time period of oscillation of this decaying oscillation can be determined by the frequency term inside the sine term of equation 5. And based on that, you can find that the time period is going to be 2 pi divided by omega naught, but it has an additional term in the denominator, which is square root 1 minus 1 over 4q squared. This suggests that the time period in this decaying oscillation is different from the fundamental time period t naught. In fact, it's longer. The second thing is, if one looks at the decaying envelope, which is shown in red, its functional form is basically e to the negative omega naught t divided by 2q. And you can easily look at that expression and come to the conclusion that when time marches forward from 0 to 4q divided by omega naught, that the decay envelope reaches a value of e to the minus 2 of its original value. E is the Euler number, about 2.7, and so e to the minus 2 is roughly about 13% of the original amplitude. If you take the expression for the fundamental time period, you can actually pretty easily show that in a time equal to 4q divided by 2 pi times the fundamental time period, the original amplitude decays by about 13%. So what this means is that the Q factor of an oscillator is a very good measure of the number of fundamental time periods that need to pass before the amplitude becomes roughly 10 to 15% of its original value. Larger the Q, the longer it takes to decay. Smaller the Q, the more rapidly in time it decays. As another example, what is shown in this slide is we've taken the general equation form 5 from the previous slide and provided an initial velocity of 1 micron per second. And we've written that expression, the solution shown in the previous slide, for two cases. One is a stiff cantilever in air, and the other is a soft cantilever in liquids. And the solution is plotted out over the same time scale, time range, going from 0 to 1 millisecond. And we see two very important things right away that jump out from these two graphs. The first is that in the same time period, you got many more cycles of oscillation for the high-frequency cantilever. This should come as no surprise. It's a higher frequency. You can fit in many more cycles of oscillation in the same time. The second graph, on the other hand, shows an effect which is much stronger in terms of the exponential decay of the solution. So you can see that in 1 millisecond, the high Q oscillator has decayed by, let's say, to 1/5 of its original amplitude in 1 millisecond. The low Q oscillator, on the other hand, has decayed virtually to 0 amplitude at the end of 1 milliseconds. Now that we have talked about what happens to the probes when there are no forces acting on them and they're just allowed to settle on their own, under their own conditions, we now are going to start talking about exciting the cantilevers, because after all, we're going to be exciting the cantilevers near resonance and amplifying the motion due to the natural resonance of the cantilevers. In dynamic atomic force microscopy, there are many, many different ways by which you might be able to excite cantilevers. On the top left is shown a common method, probably the most common method, which is the ditho-piezo excitation, or sometimes called acoustic excitation as well. How it really works is there's a piezoelectric element that sits very close to where the chip holder is located. And a high-frequency signal is applied to this piezo, which generates a mechanical motion at that frequency. That mechanical motion gets transferred from the piezo to the interface material, to the chip holder, to the chip, and it causes the base of the cantilever to move up and down. And you can imagine if the base of the cantilever moves up and down at a frequency close to the natural resonance of the cantilever, not surprisingly, we're going to expect a resonant amplification of the motion. This method is often called a base excitation kind of a model, because what you end up doing is you end up applying a oscillating displacement to the base of the cantilever. A second common technique is shown on the top right. This is a magnetic excitation in which one applies a magnetic layer on the cantilever and applies an oscillating magnetic field. And depending on the orientation of the magnetic moments, one generates a magnetic torque or a magnetic moment or a magnetic force, which fluctuates in time. And if that is tuned to the resonance of the cantilever, again, one gets large amplitude motions. On the bottom left is shown a cantilever which uses Lorentz excitation by using triangular cantilevers over which a conducting path has been metallized, has been placed in a metallized layer, and an alternating current is passed through it. There's a permanent magnetic field, and the presence of an alternating current causes a Lorentz force, which is going to make the cantilever oscillate. On the bottom right is shown an example or a figure that shows photothermal excitation. This is a method that's being developed for applications in liquids these days for many reasons that we'll discuss later. But effectively, one uses a pulsed laser that hits the cantilever, providing localized heating of the top surface of the cantilever. There is a thermal stress gradient that is set up that actually causes the cantilever to bend. And if the pulsing frequency is made equal to the resonance frequency of the cantilever, one again gets a large amplitude motion. The key difference between the acoustic or ditho-piezo excitation that's shown at the top left and all the other excitation methods is a very simple difference. While the ditho-piezo applies a displacement to the base of the cantilever, all the other methods apply a force directly to the cantilever. And this makes a very big difference to how we model and sense cantilever dynamics in these different situations. So what we're going to first do is extend our point mass model to the directly excited cantilevers, which are the magnetic, the Lorentz force, thermomechanical excitation methods. If one were to make an equivalent point mass model for this system, one needs to include the external force. And the external force here has been included in the free body diagram as F sub ext as a function of time. This is an effective force, again, and to have the motion of this point mass oscillator be exactly the same as what you would get in the actual system, there is a equivalence principle here as well. And that principle is simply that one has to choose a value for F effective such that in a given motion of the tip, the work done by the effective force be equal to the work done by the applied moments and torques in the actual probe as the tip of the actual probe goes through the same motion. Now, this can be done based on fundamental mathematical models, but what we'll show later in the class is you can determine the effective external force by some simple experimental measurements without having to resort to fundamental models of excitation and cantilever bending and so on. So if one applies Newton's laws of motion to the free body diagram shown on the top right, we are able to recover the equation of motion for directly excited point mass models of the cantilever, which is shown in equation 6. This is, of course, a canonical form of what's called a forced oscillator. In the next slide, we're looking at acoustically excited cantilevers, in which case the base of the cantilever is made to move up and down. When one looks at the equivalent point mass model for this, the block from which the spring of the point mass model is suspended must move up and down since it represents the base of the cantilever. And let that motion be z sub base. Now, that motion that we've put into the base, into the point mass model, is actually an effective motion. It's not the true motion that the actual cantilever experiences at the base of the cantilever. And again, not surprisingly, there's an equivalence principle here in that the work done in moving the base of the cantilever up and down in the actual system must equal the work done by moving the base up and down in the point mass oscillator system. And so the effective base motion is not going to be the same as the actual base motion in the real cantilever. And again, later in the class, we're going to talk about ways by which you can actually determine the effective base motion simply by some simple experimental measurements. So the main difference this has on our equations of motion is the following. That the spring force now is going to involve the difference between the absolute motion of the tip, which is Q, minus the Z motion. That tells us the compression of the spring. And so the spring force changes to be K times Q minus Z base. A second important thing to note in this free body diagram is note that the viscous dashpot is now anchored to a fixed point in the figure in the middle. What this represents is the viscous dashpot represents losses due to drag as the cantilever tries to oscillate and move in a surrounding fluid. And the surrounding fluid is assumed to be quiescent or not moving in the absence of cantilever motion, which is why we take this dashpot and anchor it to an unmoving base to represent drag aerodynamic or drag due to gas damping. When we write the free body diagram and write the equation of motion by applying Newton's laws of motion to the point mass, we get equation 7. And dividing through by k, we see that the right-hand side simply involves the z base, which is the effective motion of the base. This is great. We've got a nice equation of motion, except for one complication, and that complication is, in an atomic force microscope, when we are doing acoustic excitation, we're not actually measuring Q. In fact, we're measuring Q relative, which is the difference between the absolute position of the tip Q and the Z base, the base excitation. To explain this, let me go to the board and try to describe this using this figure here. On the left, we have a situation where the motion of the base of the cantilever is this. Let us assume that there is no bending of the cantilever, in which case the tip would move up and down by an amount Q. However, you may recall from part 1 of the course that we measure cantilever deflection using a photodetector setup. The laser comes, reflects off, goes to the 4-quadrant detector. What happens in this case is we have as much Q motion as we do Z base. However, we have no rotation of this cantilever, no bending. As a result, the reflected photodiode spot, the spot in the photodiode, is not going to move up and down a whole lot. It'll all effectively remain pretty much stationary. On the other hand, if you do have a bending of the cantilever, and if this is Z base, and this is Q, the absolute motion of the tip, what the photodiode really measures in an AFM is not the absolute motion of the tip, Q, but rather just the portion that leads to bending, and that's going to be QREL, where QREL equals the absolute displacement of the tip minus Z base. So if we make the substitution of QREL equals Q minus Z base in equation 7, one comes up with equation 8, which is the equation of motion in terms of the observed motion in a photodiode in an atomic force microscope. Thank you, and we'll continue a discussion of this in the next lecture.